All right, guys, in this video, we're going to look at finding the angle bisector between two vectors. And in general, we can actually use this nice simple formula in order to find the angle bisector. As you know, with most formulas that we use, we want to be able to prove that it actually works in any case using arbitrary values before we actually go ahead and use it. So this video is going to center around that proof. Before we get to that, we need to look at a couple properties of dot products. All right, so the first property of dot products that we want to look at is essentially if we take the dot product of a vector and the sum of two vectors, so v dot quantity vector A plus vector B, essentially that follows the distributive property. And that dot product kind of gets distributed to both the first and the second vector, and we get the sum of the dot product. So you know, pretty standard use of distributive property here as it relates back to multiplication and addition. So what we want to do is we want to show, we're not going to give a formal proof here, but we'll use arbitrary values just to kind of show that it works no matter what you're using here. So I defined V and A and B based on arbitrary components here for each one. And so we want to make sure that this actually works. So V dot A plus B, we're going to look at that first, the left side of this. And just use those components. We know that A plus B is going to be another vector. And that vector is going to be A1, B1, sorry, A1 plus B1, comma A2 plus B2. All right, and then we look at the dot product of those things. And so we know the dot product is going to be V1 times A1 plus B1. And we're going to add that to V2 times A2 plus B2. So simplify a little bit further. We distribute this. We've got V1 A1 plus V1 B1 plus V2 A2 plus V2 B2. And so we're going to use the commutative property to just kind of move some stuff around. Remember, ultimately, we're just trying to show that it's equal to this thing over here. So what we want to do, if we want to come up with the expression V dot A, then we want our V1 A1, that's here, and V2 A2 to be grouped together. So just kind of moving some stuff around. There's our two for V dot A. And then the second part is V1 B1. That comes from here, and V2 B2, and we add those two together. And so finally simplifying, we know that this expression right here is just V dot A. And we're adding that to V dot B. And so we've shown that it works no matter what your components are. So again, just to summarize, essentially when you have a dot product of the sum of two vectors, we can kind of follow that distributive property accordingly. All right, let's check out our second property of dot products here. Property number 2, we want to find an equivalent expression for the dot product. So we're going to kind of go through this and discover what this property is. If V is V1, V2, then we can find the magnitude of V relatively easily. That's going to be the square root of V1 squared plus V2 squared. All right, so we want to find an equivalent expression or find an expression as it relates to this up here. So what we want to do is take a look at what happens when we find the dot product of a vector in itself. So based on this definition of the components up here, V dot V would look like this. It would be the first times the first plus the second component times the second component which is simply equal to v1 squared plus v2 squared. Well, that looks really familiar, and if we look back up here at the magnitude of v, that's essentially the radicand of this thing. That's what's on the inside of the radical here. And so what we can say is that v dot v, and this is our property, is really just equal to the magnitude of v, but it's not the magnitude of v, it's actually the magnitude of v squared. If we take that expression and square it, get rid of the square root, that gives us our dot product. So the magnitude of v squared, so v dot v, or any vector, the dot product of any vector in itself is equal to the magnitude of that vector squared. All right, so we have our two properties. Let's go back to the original purpose of this video here. So we've got, essentially what we're trying to do is we've got this expression for the angle bisector, and that's this guy right here. And we want to prove that it works no matter what vectors we're using here. So given vectors v and w, the angle bisector of v and w is given by this expression, and we're going to define the angle bisector as vector b for our purposes here. So let v and w exist, b exist, and let it equal this expression. And so what we have to do is essentially prove that vector b is the angle bisector, or bisects the angle formed by v and w. So that's what we're going to set out to do down here. So let's start with the little diagram here. So we're going to let v and w exist. We'll just draw kind of like arbitrary vectors. Here's v, here's w, and here's vector b cutting these in between. Actually, let me draw this a little bit bigger. So let's say here's v, here's w, and here's vector b. Hopefully I can split these in between. Here's vector b. And so what we're saying is, based on what this is defined, or what we've defined here, alpha is the angle between v and b. So here's alpha. Beta is the angle between w and b. So there's beta. And there's our vector b, which we're going to show is the angle bisector. So this entire proof, before we actually get into the proof, essentially what we have to do is if b is the angle bisector, all right, let's use one additional piece of info that we defined up here. We let v and w and b exist, and we also defined what b is. B is that expression, so we can go ahead and substitute in. So substituting, for vector b, we can rewrite these two equations as v dot, and remember it's the magnitude of w times v plus the magnitude of v times w, that's our expression, and hopefully that thing kind of jumps off the page. That's that whole distributive property that we just talked about, and we'll get to that in a second here. So there's the left side, the right side similarly. W dot b, we're just going to substitute in for b, so we have w dot magnitude of w times v plus magnitude of v times w. And that's all over the magnitude of w times the magnitude of b. A lot of writing in this one. So like I just mentioned, we're going to make use of that dot product property that we just talked about. So it's kind of like the distributive property, where if we have one vector dotted with the sum of two vectors, then it essentially just distributes to those two. So let's go ahead and we're going to refer to this as property 1. So we can just kind of say like by dot product properties. Property number 1 that we looked at earlier in the video. Properties. We can simplify this. So we've got v dot this thing, and essentially we're just going to distribute that. So we're going to have v dot magnitude of w times v plus v dot the second expression in here, magnitude of v times w, and denominator stays the same. Okay, the right side here is again distribute. So we've got w dot magnitude of w times v plus w dotted with magnitude of v times w. That's all over the magnitude of w times the magnitude of b. So the next step in this is essentially we're going to rearrange this, and we're allowed to do that more or less because dot products are commutative. So by commutativity of dot product, we can rearrange these things. By commutativity of the dot product, or in other words, the dot product is commutative, we can rearrange some things. So this left equation here, we can rearrange these two, and hopefully you see why I'm doing it. And now we've got v dotted with itself, and we know a property how to use that thing, times the magnitude of w plus v dot w times the magnitude of v. Denominator stays the same. And the right side, same thing here. We've got w dot v or v dot w. Doesn't matter what order we write these in, we'll get the same thing either way because it's commutative. Plus w dotted with itself. All that over the magnitude of w times the magnitude of vector b. And we've got v dot v, and we know what that is, and we've got w dot w, and we know what that is. So we're going to use that property again, using the property of dot products. Just add a little statement just so people kind of know what we're doing here. V dot v is going to be the magnitude of v squared. So again, just to reference what we did earlier in the video, here's what we showed works for any vector. Any vector dotted with itself is going to give you the magnitude of that vector squared. And that's going to be times the magnitude of w plus v dot w times the magnitude of v. Clean that up a little bit so we don't get confused. And that's over same denominator. And then the right side, same thing. It's going to be v dot w times the magnitude of w plus, here's where my property comes in, w dotted with itself is just the magnitude of w squared times the magnitude of v over the magnitude of w, magnitude of b. So just a brief comment. We're doing a lot of writing, and anytime a proof is long and has a lot of writing to it, sometimes we want to step back and just think, what am I trying to get to? And ultimately, just remember, if B is the bisector, we want to show that alpha is equal to beta. So we've done all this stuff, and essentially what we want to do is show that this expression is equivalent to this expression. And if we're able to do that, going back up to the top, what we started with was the cosine of alpha and the cosine of beta. So if we can show that these two are equivalent expressions, essentially we can say that alpha is equal to beta, since the cosine of alpha is equal to the cosine of beta. All right, moving on. So let's take a look at what we have here. We've got magnitude of v squared. We've got magnitude of v, magnitude of v. What we can do is we can cancel these out. So we would essentially just, because the magnitude of v is just a scalar, we would be able to pull one of those out in the numerator. We've got one in the denominator, so we can cancel that. The square drops off, that drops off. And the same thing happens over here. We've got the magnitude of w in every one of these expressions, and so we can cancel one throughout. So really we're just simplifying. We have the magnitude of v times the magnitude of w plus v dot w over the magnitude of b. So that's what the cosine of alpha is equal to. Over here, remember this was the cosine of beta. And if we simplify that, we already crossed our stuff off here. We've got v dot w plus the magnitude of w times the magnitude of v. All that over the magnitude of vector b. So ultimately, if we look at these two expressions, again, because of the commutativity, addition is commutative, we can just switch the order. And so what we've got is two equivalent expressions. So therefore, cosine of alpha is the same exact expression as cosine of beta, so they have to be equivalent. And hopefully something that's relatively trivial, if we took the inverse cosine of both sides, that would undo that cosine function and leave us with alpha equals beta. So we've got our two angles are exactly the same. Ultimately, that means that B has to be the bisector because it cut it into two equivalent angles. Thus, B equal to the magnitude of W. Remember, this is what we started with and defined B as, plus the magnitude of V times W is the bisector, angle bisector of vectors V and W.